So in this video, we're going to go over section 3.6 from our textbook, which talks about related rates. And so these guys are all going to be word problems that essentially relate the rates of change of our variables. So let's look at this first example here. We're going to go over related rates in motion. So we're told that a 26-foot ladder is placed against a wall, and this is shown here. And if the top of the ladder is sliding down the wall at 2 feet per second, we want to find at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet from the wall. So we're going to break this down a little bit. We're given that the top of the ladder is sliding down the wall at 2 feet per second. If you notice from our diagram here, we have from the top of the ladder to the bottom of the wall, this distance is given as y. And we're told the top of the ladder is sliding down the wall at a rate of 2 feet per second. So that means the rate that this distance y is changing is 2 feet per second. Then we're asked to find the rate that the bottom of the ladder is moving away from the wall. So looking at this diagram, the distance between the wall and the bottom of this ladder is x. And so if the bottom of the ladder is moving away, then this distance here is changing. And we want to find the rate that this distance is changing. So we want to find the rate that this distance, or x, is changing. We want to find the derivative of x, so x prime. And we want to find the derivative of x when the bottom of the ladder is 10 feet away from the wall. And we know that the distance of the bottom of the ladder from the wall is x, so this means we want to find x prime when x is equal to 10. Okay, now notice the distance, this x here, is going to be changing with time. The bottom of this ladder is moving at a certain rate, then this distance x is going to change with time. So x is a function of t. And then similarly, the distance here, this y, is also going to be changing with time if this ladder, the top of the ladder, is moving at a certain rate. So x and y are both going to be functions of time. Now the next thing we want to do after we've identified everything is we want to find an equation that will relate these variables and apply to this specific situation. And this might be a little obvious because we have this triangle here. We have this one side distance y and this other side distance x. And we also have the hypotenuse of this triangle shape, which is the length of this ladder, which is 26 feet. So the equation that will relate our variables x and y is the Pythagorean, I think I spelled that right, theorem. So that says if we have two sides, right, so if we have y and x squared plus y squared is going to be equal to the hypotenuse squared, so this long side squared, and we know that that hypotenuse is 26 feet. So this is our function, and if you remember from the last video, this is in fact an implicit function. And we know if we're trying to find x prime, then we're going to have to take the derivative of this guy and solve for x prime, because that's what we're trying to find. So what we'll do is we'll take the derivative of this function with respect to t, because both x and y are dependent on t, so t is our independent variable. So we're going to take the derivative of this function with respect to t. Alright, then we know from implicit differentiation and the fact that we have a function of t squared, so what I mean by this is And we know that the derivative of a constant squared is just going to be 0. The constant squared is still just a constant. And so since we have a function of t inside of a power function, and we're going to differentiate with respect to t, we have to use the chain rule along with implicit differentiation here. So we're going to have 2 times x of t times the derivative of x of t with respect to t, then plus 2 times y of t times the derivative of y of t with respect to t. Right? So we're just taking the derivative of both of these guys using the chain rule, which says we're going to take the derivative of our outside function. So this 2 comes down in front, and it will be evaluated at our inside function, and then we'll multiply it by the derivative of our inside function. All right. So writing this a little nicer, I'll just drop this x of t notation. So we have 2x times dx over dt plus 2y times dy over dt. And this will be equal to 0. So this will be our related rates problem. So both dy dt and dx dt are both rates, and they're related by this problem. Now remember, what we want to do is find x prime, and we know that that is the same thing as dx dt, so we'll just solve for that guy. So we'll divide by 2x on both sides. Oh, sorry. First thing we'll do is subtract out a 2y times dy over dt. So we'll get 2x times dx over dt is equal to minus 2y times dy over dt, and now we can divide by 2x. So then we get dx over dt is going to be equal to 2y dy over dt divided by 2x. And then we'll drop the dy over dt notation just so it's a little bit nicer. So we'll get x prime is equal to 2 minus 2y y prime over 2x. All right. So this is x prime. And so what we can do is just plug in our known values, right? We were told that we want to find x prime when x is 10 feet. And then we're also told that y prime is going to be 2 feet per second. So, okay, so what we can do is plug that into our equation that we got for x prime. But before we can do that, notice that we weren't given any information about y. So what we can do is just use our implicit function here, plug in 10 for x, and then get our y value. So I think I'll write this over here. So when x is equal to 10 feet, we'll get 100 plus y squared is equal to, this will be 676. Then taking out 100 from both sides, we'll get 576. And then squaring this on both sides, we'll get 24. So this means when the bottom of the ladder is 10 feet away from the wall, this distance y here is going to be 24 feet. And so now we have y prime, y, and x. We can plug this into our equation and get our answer. So we'll get 4.8 feet per second. So this means that the rate that the bottom of the ladder is moving away from the wall is 4.8 feet per second. So this distance is changing at a rate of 4.8 feet per second. So with that, here is the formal definition or procedure of solving our related rates problem. So first we'll sketch a figure if it'll be helpful. And as you saw in the last example, it is pretty helpful to have a diagram to refer to. Then we're going to identify all relevant variables, including those whose rates are given and whose rates are to be found. So just how we did in the last example, identify what's given and what we're trying to find, and all the other variables that are relevant. Then we're going to express all given rates and the rates that need to be found as derivatives. And step 4 is very important. We need to find an equation which connects the variables identified in step 2. And that's what we did with the Pythagorean theorem in the last example. Then we'll implicitly differentiate the equation that we get for step 4 and substitute all given values and then solve for the rate that we are trying to find, the unknown rate. All right, so let's look at another example. We're told that 2 motorboats leave from the same point at the same time. If one is traveling north at a distance, or north at a rate of 15 miles per hour, and the other is traveling east at a rate of 20 miles per hour, we want to find how fast the distance between them will be changing after 3 hours. Okay? So let's identify what we're given. One of the boat is traveling north at 15 miles per hour. We also have this diagram here. So north direction, the distance from this point heading north is going to be y. So north to our y direction. And I guess I shouldn't say y direction. North is the direction and y is our distance. So y is going to be the distance from this point that the boat started at to where it is at some given time. So then this tells us if the boat is traveling north at a rate of 15 miles per hour, so this distance here is changing at a rate of 15 miles per hour. So this means dy dt is going to be 15. Right? So every single hour, y is changing by 15 miles. So y is a function of t. Similarly, we're told that the other boat is traveling east at a rate of 20 miles per hour. And from our diagram here, east is in this direction, and our x value represents the distance this boat is from this point at some given time. So x again is going to be a function of time. And the rate that distance is changing is 20 miles per hour. And so we want to find how fast the distance between these boats will change after 3 hours. If you look at our diagram here, the distance between these 2 boats is going to be z. And so we want to find how fast the distance between them is changing. So this means we want to find the rate of change of that distance after 3 hours. So this means when t is equal to 3. Alright, so x, y, and z are all going to be dependent on t. And again, we have this triangle shape here, so we'll use the Pythagorean theorem to relate these variables. So we have that x squared plus y squared is going to be equal to z squared. Alright. Now in this case, we don't have a value for z. In the last example we were given that, but that's fine. We can still take the derivative of this using implicit differentiation. And again, since we have the square of these functions here, so a function within a power function, we'll be using the chain rule as well as implicit differentiation. So let's take the derivative on both sides of this guy. So we know this will be 2x times dx dt plus 2y times dy dt. That'll be equal to 2z times dz dt. All right. And then solving for dz dt, remember, this is what we want to find. We can just divide by 2z here. So this means dz dt is going to be equal to this. All over 2z. All right. Now we were given dy dt and dx dt, so we can plug that into our equation here. But we weren't given any information for x and y. Now what we can do in this situation is we can actually just make up values for x and y. And what I mean is that whatever I plug in using our equation, our Pythagorean theorem here, whatever numbers we plug in for these guys, for x and y, we'll get a z that's related to these guys. So the ratio between these three variables will stay the same no matter what numbers we pick here. So I'm just going to let x be 4 and y be 3, just so we have nice numbers. So if I plug these guys into our Pythagorean theorem, we get 16 plus 9. So we get 25 is equal to z squared. And then taking the square root on both sides, we get that z is equal to 5. Okay. So this tells us the distance in this direction is 4, and in this direction it's 3. Then the distance between our two boats will have to be 5. Okay. If you were to choose different numbers for x and y, we would get a different value for z, which would still be related via this equation. Okay. So we can just use these points here along with our values for dy dt and dx dt. So we'll do z prime, we get 2 times 4 for x times 20 for dx dt plus 2 times 3 for y and 15 for dy dt, all over 2 times 5 for z. Then this equals to 160 plus 90, all over 10, and this is equal to 25. So z prime is equal to 25, and this will be feet per second. And so we can interpret this. This is pretty much telling us that the boats are separating at a rate of 25 miles per hour. So sorry, I totally forgot what units we were using. Of course, it's miles per hour. The last one was feet per second. So the boats are going to be separating at a rate of 25 miles per hour. And the second part of our question is we want to find the rate that this distance will be when t is equal to 3. So what we can do is plug this in for z prime. So after 3 hours, the boats will be, we know that the distance is changing at a rate of 25 miles per hour. So every hour it's changing by 25 miles. So we'll just do 25 times 3 to see the distance after 3 hours. So that'll be 75. So after 3 hours, the boats will be 75 miles apart. All right. And this is the second part of our answer. Okay, so let's look at another example here. We're told that a point is moving along a graph, and when the point is at this point here, its y-coordinate is going to be decreasing by 2 units per second. And we want to figure out how fast the x-coordinate is changing at that moment. So a couple things to note here. Y-coordinate is decreasing by 2 units per second. So this immediately tells us that dy dt is changing over time, so it's a function of time. And the rate that it's changing over time is 2 units per second. And then we want to figure out how fast the x-coordinate is changing at that moment. So this will be dx dt. The x-coordinate is also going to be changing over time. And so this is what we're trying to find. Something to note for this example, though, is that we're actually already given our equation that relates our variables x and y. So that'll be useful. We're given our equation here. And again, we know dy dt, and we want to find dx dt. So we'll do that by taking the derivative of this. And again, we'll use implicit differentiation because x and y are both functions of t. So they are dependent on what the value of t is. X and y are both changing with time. And we also have these power functions here. So our function y of t and x of t are both inside power functions, so we're going to be using the chain rule as well as implicit differentiation. So we'll take the derivative of the outside of this, evaluated at the inside function, which is y. So that would be 3y squared, right? So just doing the power rule, the 3 comes down in front, and then we have 3 to the power, or y to the power 3 minus 1. So that is the derivative of our outside function evaluated at our inside function, and then we still have to multiply it by the derivative of our inside function. And doing the same thing on this side. Then solving for dx dt, just divide by 2, so we get 3y squared times dy dt over 2x. Alright. Now we want to solve for dx dt, so let's see what information needs to be plugged into here. We need to plug in dy dt, which we were given. We also have this y and this x. And if you notice, back in this problem, we were given a coordinate for y and x, so we can just plug that in here. So we get that dx dt is going to be equal to 3 times our y coordinate, which was 4, times dy dt, which was just 2, all over 2 times our x coordinate, which was negative 8. So we'll get 96 over minus 16, so that'll be negative 6. So this tells us that our x coordinate is decreasing by 6 units per second. All right. Actually, sorry, I just noticed a typo here. Going back to our problem, we have to be careful with the wording here. So it says the y-coordinate is decreasing by 2 units per second. So this means our dy dt, is actually equal to minus 2 units per second. So if we go back here and we plug in that value for dy dt, these negatives will actually cancel. And so we still end up with 6, but our answer changes slightly. We find that the x-coordinate is going to be increasing by 6 units per second. All right, so yeah, just be careful with the wording. It is easy to miss something simple like that. All right, and then the last thing we're going to look at is this problem here. So we're going to look at related rates and how it's related to business. So suppose that for a company manufacturing flash drives, the cost, revenue, and profit equations are given by these guys here. And we're told that the production output in 1 week is X amount of flash drives, and if the production is increasing at the rate of 500 flash drives per week, when production is 2,000 flash drives, we want to find the rate of increase in the cost, the revenue, and the profit. So we're looking at essentially the amount of flash drives is changing over time. So this tells us that the production is going to be a function of time. So t is our independent variable in this example as well. And so this means our cost, our revenue, and our profit are all going to be dependent upon time, so they're all going to be functions of time. So if we want to find the rate of increase in these guys, we're going to find the rate of change of the cost with respect to time, the rate of change of our revenue with respect to time, and the rate of change of our profit with respect to time. And we'll look at all of these guys when production is going to be increasing at a rate of 500 flash drives. So the rate of change of production over time is 500. And then the production is 2,000 flash drives. So X is equal to 2,000. Because X represents the amount of flash drives. So if it's changing at a rate of 500 flash drives per week, that's dx dt. And if production is 2,000 flash drives, that means X is going to be 2,000. All right, so we got everything set up. Now let's find our answers. So we're going to find dc dt. So that's going to be equal to the derivative of our function c with respect to time. So we're going to take the derivative of this constant with respect to t, so that's just going to be 0. And the derivative of 2x with respect to t, remember we're going to take the derivative of our outside, so that would just be 2 times the derivative of our inside function. And then we want to find dc dt when dx dt is 500. So this tells us that our cost is going to be increasing at a rate of $1,000 per week. All right. Now we want to do the same thing for our revenue. We want to find the rate of increase in revenue when X is 2,000 flash drives, and the rate of change of that guy is going to be 500 flash drives per week. So we'll take the derivative of our revenue equation. So dr dt is going to be the derivative of our revenue equation, which is 10x minus 0.001 x squared. So we're going to take the derivative of 10x, so that'll be the derivative of our outside, so 10 times the derivative of our inside with respect to t. Then here we're also going to do chain rule. Remember, because we have a function, x of t, inside our power function. So first we'll take the derivative of our outside function, so this 2 will come down in front and multiply this 0.001. So that'll be 0.002. And this will be evaluated at our inside function, and then we'll multiply by the derivative of our inside function. And then we want to find dr dt when the rate of change is 500 and our x is 2000. So here we'll get 5,000 minus 2,000. So this is $300, $3,000 per week. And so this tells us that the revenue is increasing at a rate of $3,000 per week. All right. And then lastly, we want to find the rate of change of our profit. And so our profit equation is just our revenue minus our cost. So this means dp dt is going to be dr dt minus dc dt. So what we're doing is just taking the derivative of this guy with respect to t. And so we get this here. And we already know from parts A and B what dr dt and dc dt are, so we can just put those in there. Dr dt, remember, at 2,000 flash drives changing at a rate of $500 per week, we found that dr dt was 3,000. And we found that the cost at 2,000 flash drives with a rate of change of 500 flash drives per week was $1,000 per week. So this tells us that our profit is going to be $2,000 per week. So our profit is increasing at a rate of $2,000 per week. All right, so that's it for this video. With related rates, definitely just be careful with reading the problem as we saw here, and then make sure to follow these procedures.